So I wanted to make a video sort of as a precursor to my RSA hardware implementation. I've been quite busy the past couple of weeks as well, so I actually haven't started that project at all. But I felt as though it was quite important to get a solid grasp of the theoretical underpinnings before I actually attempted that project. It doesn't seem too difficult, but okay. And so I wanted to make a video then sort of covering or giving you an introduction to asymmetric cryptography. And at the very least, you should have a solid roadmap of how things are. And so if you want to further explore, I think it should be easier if you at least know where you're going. So I'll start off by talking about something called cyclic groups, right? And then we're going to talk about the Diffie-Hellman key exchange. Right, so that'll be pretty much your introduction to asymmetric cryptography. And then we'll talk about a little bit about Fermat's little theorem, and that's actually heavily related to cyclic groups, right? In fact, I think Fermat's little theorem sort of describes a cyclic group. And then we can go on and just explain a little bit how RSA works. I think a good amount of you should know how RSA functions. At the very least, it's just a simple algorithm, right? And it's actually based on Euler's theorem, so we'll go over a proof for Euler's theorem. I think it's very important you see the proof, and then obviously once you see the proof for Euler's theorem, you can understand that, well, it's just a generalization of Fermat's little theorem, right? So I think this is like your one ring to rule them all kind of thing, where this is concerned. And then there's a little remark I'll make as well about Chinese remainder theorem. I won't get into that here, but RSA is actually based on Chinese remainder theorem. Euler's theorem is sort of just a simplification, if you want to put it that way. But for the most part, it does show, right? So I think it's quite helpful to think about it in that way. So let's start off with cyclic groups, right? So what is a cyclic group? And this is probably just going to be me throwing you into the deep end of the pool, right? And so let's just assume we had some base raised to an exponent, right? And let's reduce modulo 11, okay? And so, by the way, why modulo 11? So we're going to assume, right, we're in a group, you call it Z11 star, and you guys should be familiar with this, I hope. If you don't know, Z11 star, all that means, right, is the Euler's totient function. That's literally what Z11 star means, right? So, but Euler's totient function is going to return the group cardinality, right? How many elements inside of this group are relatively prime to 11, right? And so Z11 star would actually just be everything except 0, right? You just kick the 0 out. So it's 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, right? So all of these numbers are relatively prime to 11, right? And if you don't know what relatively prime means, well, they just have GCD condition, right? GCD equals 1. That condition is true. So, and if you don't know how to do GCD, I think you should probably go look that up. But there's the Euclidean algorithm, there's the extended Euclidean algorithm for finding GCD. But really, conceptually, it's very simple. For instance, if I took 1 and 11, right? And what is the greatest common divisor, right? Well, it's 1, right? Okay, and same thing for 2. Greatest common divisor between 2 and 11 is 1, and then you can go through the entire list. So in principle, that's how Euler's totient function works, right? And so phi of n is going to return 10 in this case, right? So and that's the group cardinality. I'll just say group cardinality. Okay, and you'll see quite literally Z11 star is 10 elements in the group, right? So we're going back to our example here. And so I'm saying a raised to something, right? And what is a? You're probably thinking. So we'll say a is equal to 3, right? So our base is 3. So it's like 3 raised to the first power, right? And I don't have the congruent. We'll just assume, right, that this equal sign means congruent, right, or is equivalent to, okay? And this should be very short, so I think this is 9 mod 11, fairly simple, a raised to the third. So that's 27 mod 11, so that's like 5, right? Yeah, that makes sense. And a to the fourth, well, what is that going to be? Well, that's just a to the third, right, times a, which is equal to 5 times 3 right? Because we just computed a to the third as 5. And all reduced modulo 11, so this is just 4, right? And then a to the 5th is, forgot the equal sign here, a to the 5th. And you can see where I'm going with this, pretty much. We're just increasing the exponent, right? We're not doing anything fancy here at all. So this is just a to the 4th times a, right? And this is equal to 4 times 3, right? Yeah. It's equal to 1. Right, so that's 12 mod 11, so it should be 1. Okay, now let's do a to the 6th, right? And something pretty special is going to happen here. And if we do a to the 6th, right? What is this? This is just a to the 5th, right? Times a, right? What is that? What is a to the 5th? It's just 1 times a, right? 1 times a. So that's 1 times 3, right? So, yeah, it's just 3. So, did you notice something here? When we reached, right, this, oh, wrong one. Oh, I don't know what's going on there, but okay, that's a bit weird. But when we reach this stage here, why is it so weird? Oh, because I have this square box selected. Okay, can I undo that? Sure. Yeah. So when we got here, right, something really, really weird happened, right? This a to the 4th, right, collapsed down into 1, and then so when we went over to the next one, when we tried to pick up a to the 5th, it's already 1, right? And so if you look at this value here, 3, it's the same as this value here. Okay? And this pattern is actually going to repeat itself over and over again. Right? And so we're going to get 3, and then if we computed a to the 7th, we're going to get 9, 27, so on and so forth. And so this, right, is called a cyclic group. And so we've already touched on cyclic groups there already. And I have a better example I sort of prepared for you, and it's with the the base is 2, right? A is going to be 2 in this case, right? And so if you look very carefully, but this time it's much longer, right? Here we can see that the cycle length, or you call that the order, right? The cycle length was very short, right? We just did like a couple of calculations and then the cycle repeated very early. But here the cycle length is much longer. In fact, right, if you look very carefully, let's go back here. Let's go back here for a second. What are the numbers that we generated? Right, so we generated 3, right? We generated 9. We generated 5. We generated 4. And we generated 1. Okay, so inside of this set, these are the numbers that we generated. So it's clear then that using this base 3, right, we didn't generate the entire set. And so what I'm trying to get to you here is, if you change the base, right, you can actually generate the entire set again. And so actually this number 2, right, it's called a primitive element, or it's called a generator, right? And it's typically denoted as alpha, right? And so alpha is your base. Okay, and so the number 2, right, is known as a generator. And why is it known as a generator? Because it'll generate the entire set for you. And you can see that here. So 2 to the 1, 2 to the 2. Look at it very carefully, right? You get 2, 4, 8, 5. So you can count and see that it goes on 10 times, right, before we get 1, right? So 2 to the 10th, right, is just 1. It's congruent to 1 mod 11, all right? And so that's going to sort of collapse down that parameter that I was showing you earlier. And so when you go over to the next cycle, right, it's just going to repeat itself, right? And so we've got 10 elements here, and if you wanted to double check, right, that each of these elements actually belongs to this original group Z11 star. Okay, so that's a cyclic group, and the parameter a that you choose, right, is known as alpha. They call it alpha, and this is actually important because I'm going to introduce Diffie-Hellman key exchange now, and this alpha parameter is important to know. Okay, and so yeah, let's go straight into Diffie-Hellman key exchange. Oh, actually, before I do that, let me talk a little bit about Fermat's little theorem. And so you guys should know that, let me just use the highlighter here just very quickly. So Fermat's little theorem is, if we have some base alpha, right, and you raise it to p minus 1, this is congruent to 1 modulo p. There. Okay, so that's Fermat's little theorem. And so I think that's fairly straightforward. And what is this trying to tell us, though, right? Now, some base, right, raised to the largest element inside of the group, right? P minus 1 is the largest element inside of the group. In this particular case, let's use 10, right? So 2 raised to the 10, right? You can quite literally see it here, is equivalent to 1 mod P. Can you see that, right? That's Fermat's little theorem describing cyclic groups. I thought that was pretty neat. So, yeah. So let's just talk about Diffie-Hellman key exchange now. So I'm just trying to sort of rush through this video. So we've got two parameters that are publicly known. Okay, to start with, so there's alpha that I was talking about. This is what's called as your generator, right? Or this is the base, right? And you've got P, and P is typically chosen, so in the set 2, 3, 4, all the way to P minus 2, right? And you're probably wondering to yourself, okay, well, isn't this just like supposed to be like the same thing here that we had, right? You could, right? You could do that, but in practice, it's thrown out. You throw out the largest element, and you throw out the smallest element inside of the group. If you're using Z11 star, for instance, right? So it is phi of n. It is that group phi of n, but you're kicking out the largest element, and you're kicking out the smallest element inside of the group as well. Okay, so how does Diffie-Hellman key exchange actually work, right? And so the first thing you do, right, if you had Alice, I think I'm just going to type because sort of trying to draw this on my touchpad is a bit much. So A, right, you choose A, and it has to be within this set here, right? So it has to be some value inside of here, right? So A is an element of P. Well, I'm just gonna just pretend this is like is an element of, right? And then B for Bob, right? Bob selects his private key, right? So we're selecting private keys. So A is a private key and B is a private key, right? And so this is also an element of P, right? So, okay, well, obviously this is just terrible notation, and I just hope I'm getting the point across to you, right? And so what they do, right, is they compute this. They compute A is congruent to, right? Again, I don't have the congruent symbol, just assume, please, that it's congruent to alpha. Maybe I can just you know, just write it out for once. So A is congruent to, I should probably just get a mouse. Yeah, that'll probably help a lot. To alpha raised to the A mod P. Yeah, this is just bad. I'm sorry. I just have to type this out. So A is congruent to, imagine it's congruent, right, to alpha. This is alpha, right? Okay, alpha, I'll type it out. Alpha raised to, and then, right, you raise that to your private key, right? So it's alpha raised to the A mod P, reduced mod P, of course, right? So this is Alice's public key, right? And then Bob does the same thing, right? So Bob computes his public key, so B is equivalent to, right, alpha raised to the B, right, mod P. Now, I hope you remember, right, what this alpha is actually doing, right? And so you're generating the group, right? You're generating the entire set. So based on whatever value you picked for A, or whatever value you picked for B, it's going to land you somewhere inside of this set, right? Somewhere inside of the cyclic group. You don't know where you are in the cyclic group, but you know, okay, well, you're somewhere there, right? And so what you do then is you send that value over. So Alice is going to send her public key over to Bob, and then Bob does the same thing as well. He sends his public key over to Alice. Now, how do you decrypt, right? Well, it's actually quite simple, and it's really interesting, actually. So what ends up happening here is what Alice is going to do is she's going to take Bob's public key, right, and raise it to her private key, reduce modulo P, of course, right? And then Bob is going to do pretty much the same thing, right? So Bob is going to take Alice's public key, raise it to his private key, and reduce modulo P. And somehow or the other, I'll show you this in a second, what they end up with is the same value, right? They end up with the same shared key, right? So how the hell does that happen? Well, actually, I'll show you now how that happens. So let's start off with on Alice's side. So I should just put A over here for Alice and B over here for Bob, just to make it a little bit more explicit, right? And so let's start off on Alice's side, right? How did Alice compute her public key, right? So Alice computed her public key as alpha raised to the A, right? And this is what she sent to Bob, right? And Bob received this public key, right? So over here on Bob's side, what is Bob doing? Bob is taking this alpha raised to the A and then he's exponentiating it, right? And so he ends up with alpha to the A, B. Okay? Reduced modulo P, of course. Just assume the reduced modulo P is there. I just don't want to do too much more drawing. And so this is what Bob is computing, right? On his end. Now Bob also, look at what Bob does. Bob computes his public key as alpha raised to the B, right? And then he sends this over to Alice. And what does Alice do? Alice takes Bob's public key, right? And raises it to the 8th power. And so what you end up with is alpha to the BA or alpha to the AB, which is the same thing as what Bob computed. So they end up with a shared key, right? And so let me just type, okay, that happens quite a bit. So so they end up with a shared key, right? And this is known as the Diffie-Hellman key exchange. And so you can actually just use that shared key, throw it into something like AES, right? And then you can just start encrypting messages in bulk if you so desired. But if you understood this, then you have a pretty strong foundation, I think, going forward with asymmetric cryptography. You can understand a lot of things like digital signatures, protocols. They're all built on this foundational idea by Diffie and Hellman. Okay, so we covered cyclic groups, we covered the Diffie-Hellman key exchange, we covered Fermat's little theorem, kind of, right? Not really, we kind of covered it. But I think as long as you understand that it just describes a cyclic group, I think that's enough, right? Now let's talk about RSA. I'm not going to actually do an example. You can do that in your own time if you'd like. It's not too difficult anyways. And so RSA, again, it's very simple, right? How does this function? So you pick two large primes, P and Q, right? So pick two large primes, P and Q, right? And then what you do is you multiply them to get N, right? So N is just P times Q. Okay, why are you picking two large primes? Well, this is a fact. You multiply any two primes, right? And you get a composite number. Okay? And this is pretty important, actually, because composite numbers are very hard to factor, and it plays into the security of RSA. Okay. So you've got this, you compute phi of n, phi of n, right? Whatever you get, right? It's actually p minus 1, q minus 1. This is how you compute it, if you know what p and q is, right? And so if you know p and q, this computation is trivial, right? If you don't know what p and q is, that's another story entirely, right? And there's actually a formula. You just have to do the prime factorization of the composite number, and then you can try to figure out, but it's hard to do, especially when you're dealing with like 2,000-bit long vectors, right? Good luck with that. Lifetime of the universe computing that thing. So, yeah. Okay, you compute phi of n, right? And why is it p minus 1? This should already be setting off some bells in your head, right? You come up back here. This is it. This is remember group cardinality, phi of n, group cardinality, right? N minus 1, p minus 1. Right? I'm hoping you see what's actually going on there. Okay. So you compute phi of n. Then you pick E, right? And E now has to be some number such that GCD, and E has to be inside of this set n, obviously, right? And GCD of whatever you pick, E and n must be 1, right? There you go. Oh, not n, it's phi of n. Phi of n, not n. There we go. Okay. All right then. And so because remember, phi of n is just giving you the largest value inside of that, your group cardinality then, right? So you can just pick something inside of that set, right? And then the reason why you're picking another value as well, such that it has GCD condition E of 1, is because you need it to have an inverse, right? So it's very important. So then what you do is you compute your private key, which is D, right? So E times D is equal to 1 modulo phi of n. Right? I hope you understand this, right? So the inverse is defined, right, as, I'll just go this over very quickly. Any value, right, a times a inverse, right, has to be equal to 1, right? By definition, that's what the inverse is. And then you just reduce modulo whatever finite set you're operating under. And so be very careful here, not modulo reducing modulo n, right? Because we're not in the finite set n, right? We're in finite set phi of n, right? So phi of n here. Okay, and so that ensures closure. And okay, that's how we compute d, right? And so now we have just about everything we need, right? We have the public key, k public, it's n and e, sent over the channel. That's your public key, right? Obviously, you need to send over p as well, right? And okay, so how does RSA work, right? So how this operates, I'll probably need a new page for this one. So let's just draw like a very scuffed diagram to explain how RSA works. So the first thing you do is you set up your key, right? Everything we just discussed there, right? You set that up. And so we can say Alice is the one doing all the hard work here, right? So your key got set up, right? And so what you do is you send this over to Bob, right? To Bob. Okay, it's taking a while to write. And so what Bob is going to do, right, is very interesting. Oh, by the way, you don't have to set up RSA every single time. For instance, if you had a hardware implementation of RSA, which I'm going to do, right, all of these parameters are sort of burnt into the chip, right, at the time it's being manufactured. So it's kind of, in a way, it's kind of like firmware, right? You do the setup and you set up once, right, and you're good to go. You don't have to set up every single time. So that's a very important thing, right? Because it is computationally expensive, especially generating large primes, and good luck with that. Okay. So Alice is going to send over her public key, right? K public. Okay. She sends over n and e, like so. Yeah, and you don't need this. You don't need that. I don't know where I got that p from. Forget about that p. This is your public key. I don't know, for some reason I was thinking like you were reducing modulo p, but no, you're reducing modulo n. But okay. So you send over e, right, that you computed, and you sent over n. And so what Bob is going to do, right, is he's going to take his message, right, convert it over into some number, right? He's going to take his message and raise it to the public key that you sent over. Reduce modulo n, of course. So mod n. Okay, so it's very simple. You take your message, exponentiate it, right? And then you reduce modulo n. Okay, and then he sends that over the unsecure channel back to Alice. Okay, so this is the unsecure channel here. So your bad guy Oscar or Eve, they're listening here. So unsecure channel. So that comes back to Alice. So your bad guy quite literally has all of this information here, right? And so what Alice is going to do is take this ciphertext that she received, right, and raise it to the power. So we'll just call this C. So she'll take her ciphertext and she's going to raise it to D, to her private key D that she computed here, right? And this is going to recover, right, the original message, okay? So, and this is how RSA works. So here you've got your setup, everything that we just discussed up here. She sends this over to Bob, right? Bob computes the ciphertext using the public key, and then Bob sends the public key over the unsecured channel. Well, the ciphertext, not the public key. He sends the ciphertext computed over the unsecured channel back to Alice, and then Alex recovers, right? She recovers what the original message was. So I hope that was fairly simple to understand. And so where does the security of RSA actually hinge, right? What doesn't Bob know? Bob doesn't know D, right? He doesn't know D. Otherwise, he could obviously just recover the message. It would be a useless algorithm, right? So a useless cipher system. So how is D being computed? And so if you look back up here, D is being computed as the inverse of E, right? And in order to find the inverse of E, you need phi of n. Remember, your attacker Oscar only has n. He doesn't have phi of n. And so this, right, And again, this is where I mentioned before, you get a composite number, and you choose two very, very large primes, right? And so the composite number that you get is going to be practically impossible to factor, right? And so he can't recover phi of n. If he can't recover phi of n, he can't compute the inverse. If he can't compute the inverse, then, well, okay, good luck, right? You're not going to be able to read the message. And so this is actually what makes RSA so secure, right? Alright then, so the only thing left for me to cover now is Euler's theorem and how that ties into RSA. So we've done RSA, let's talk about Euler's theorem now and how that ties into RSA. And then we're going to do a proof for this. I'm going to prove to you why this decryption works, right? Sure, I'm telling you that it works, right? But it's not actually entirely obvious that this should actually work. Okay, it makes sense. Okay, D is the inverse of E, and maybe, you know, there's something there, but I think it helps to sort of see like mathematical concrete proof of what's going on. So I have this very simple proof of Euler's theorem, and so I'll just start off by going it through and sort of explaining it. And so it said, consider the set of all numbers less than n relatively prime to it, right? So that's a1 up to a phi of n, right? That's Euler's totient function, right? The set of all numbers less than n and relatively prime to it. So that's the set, right? That's a set of Euler's totient function. Okay, Euler's totient function gives you the cardinality of this set. Okay, and so for Z11 star, that would have been like 1 all the way up to 10, right? For instance. And then so we consider another number c, right, that is less than n and relatively prime to the set as well. Well, obviously then, right, if c is less than n and it's relatively prime to it as well, then c is an element of this set, right? Okay, whatever c is, it could be anything, it has to be an element of this set by definition, right? It's relatively prime to n, right? It's less than n. Okay, well, it's an element of the set. Okay, that's fairly simple, I think. And so first observe, right, and this is the thing that you have to sort of understand, and thanks Dr. Fazil for taking some time to explain this to me. Actually, I didn't know anything about Euler's theorem, and so I sort of just asked him without knowing anything, but he did take his time to explain this to me, and I was like, oh, that makes sense, right? Even though I didn't go over the proof as explanation, he made some very, very good points that definitely helped me to understand what was going on here. So, okay, so you're observing, right, for any element inside the set, some a of I, right? And then something c times a of I. So remember we said that c is also an element inside of this set. And so essentially what we're saying here is that for any element inside of the set, for instance in Z11 star, we pick 3, right? Any other element inside of the set, right? It could be 3 as well, right? Or it could be 4. As long as it's inside of the set, it's congruent to some other element modulo n, right? And this is a true statement. And this is actually closure, right? This is multiplicative closure right here. Okay, and so if you want to go write this down, right, you can pick like, let's just do like a quick example. If we pick 3 as a of I, right? And we pick 3 to be c as well, right? Okay, 3 by 3 is 9, right? 9 modulo 11. Okay, it's congruent to another element, 9, right? A sub j is 9 modulo n, okay, inside of the group for some j. Okay, well, j was 9 in our case. So this is true since c and a are themselves relatively prime to m, their product have to be relatively prime to n as well. Okay, follows immediately from the definition, and I think I hope I did a decent job of explaining what that actually meant. And so, right, c of a sub I is congruent to c of a sub j modulo n. All right, so this bit here, so what we're trying to do is prove that a sub I is equal to a sub j. So how is that actually done, right? And so there's actually two ways that you can sort of try to think about this, I guess. And the easiest way is, right, this is true because the cancellation can be done since c is relatively prime to n. We know, right, by definition, c has to be relatively prime to n because it's a set, right? It's inside of the set. So everything inside of the set is relatively prime to n. So an inverse exists, right? Reduced modulo n, of course. So an inverse exists. So what you can do is just multiply by the inverse of c on the left side of the equation, multiply by the inverse of c on the right side of the equation, and it's going to cancel out the c's. I hope you see what's going on there. And so it's just a sub I is equal to a sub j. You know, fairly simple stuff here. And you can obviously do some transposition as well. So let me try to show you the other way if that didn't make sense to you. I think that's personally the easiest way to sort of see what's going on here. So a sub I is congruent to a sub j, very, very bad writing, modulo n, right? Modulo n. Okie dokie. So, well, what you do, right, quite literally is you just transpose this value over, right? So bring this guy over here, right? So what you're going to end up with is C a sub I minus C a sub j is equal to 0 modulo n, right? And oops, you can actually factor this now, right? You can factor this. You can factor out the c, right? And so you're left with a sub I minus a sub j is congruent to 0, okay, modulo n. I'm not going to write that back, okay? So this is probably already very, very simple to understand then, because, right, whatever value is here has to be equal to 0, right? It has to be equal to 0. Okay, and so that implies, right, that the value inside of this parenthesis is 0. No other value inside of this parenthesis will produce a, this, I don't know what you call it, a statement, if you want to call it a statement. This statement is going to be false, right? If this value is 1, 2, 3, anything else other than 0, this proposition, this statement is false, right? So it has to be 0. Therefore, it follows that A is equal to J, right? A sub I is equal to J sub I, right? Okay, if you just transpose this, then you get 0. And so C times 0, okay, 0, 0 is congruent to 0 modulo n. Right, so I hope you sort of understood that. If not, well, I don't know, maybe there's like better explanation somewhere, but I think that's fairly simple enough to follow. Okay, and so, right, hence, if we now consider the set, right, C times A sub 1, C times A sub 2, all the way up to C times A sub n, it's just a permutation of the original set, right? Can you sort of see that? I hope you can see what's going on there, right? Because if you take some element C, right, and you multiply it by that some other element inside of the set, then you're going to get another element in the set, okay? And so, by definition, right, if you take unique C's all the way up to this guy here, and it doesn't even have to be unique C's, right? It could be the same C value that you're taking, which is quite literally the definition here. It's the same C value that you're using, right? But if you multiply that by all the elements inside of the set, so from A1 all the way up to A phi of n, you're going to get a permutation of the original set, okay? That's how that works. And I don't know if you remember from when we were talking about cyclic groups, right? How when you sort of exponentiated based on a different generator, what you ended up with, right? For instance, if you used a primitive generator 2, you ended up, right, with a permutation, right, of the original group. So it's actually very similar to that. And you'll see actually then that Euler's theorem really is just a generalization of Fermat's little theorem, and so it follows then that the same thing I was showing you with the Fermat's little theorem describing cyclic groups, then follows that Euler's theorem also describes a cyclic group. So okay, we can actually write this then as sort of a product summation from k of 1 all the way up to phi of n, right? And then it's just C times A sub k, right? And so, again, this is quite literally what's just written here. I just hope it's easy enough to follow. And this is congruent to, right, we just said, same thing, A sub k modulo n. And so this permutation here, right, that we got is equivalent to the original group. Okay, so the two sets are equivalent to each other. It's just that one is a permutation of the other, okay? And then, hence, what you can do here is, so I think I need to sort of write this out, what's going on here. And so you can kind of follow what's going on. So it's this guy, k equals 1, all the way up to phi of n. So you're basically just cycling through the entire set, right? And then it's C times a sub I, right? And so quite literally what's going on here, right, is you're going to get C times, it's a sub k rather, not a sub I. I just have a habit of writing certain parameters. So a sub k, okay, because k is the variable here that we're incrementing. And so it's going to be C times a sub 1, right? And then C times a sub 2, right? Do you see what's going on here? And it's going to go all the way up to phi of n, right? And so you can see, right, that the total number of times that C is going to occur is phi of n times. So you can factor out the C's, right? And so this just becomes C raised to the phi of n. Okay, you can factor out phi of n C's. I hope that's clear, right? So you factor this guy out, right? And now you can just multiply it by the original product summation. So k equals 1 to phi of n. I'm not going to write it out. Phi of n, okay, right? Phi of n. And then you just say a sub k, okay? So these two expressions then are equivalent to each other, all right? All I did was factor this guy out. And so you can see quite literally that's what they did here. They factored out the C's, right? And it occurred phi of n times. And then, okay, it's just the same thing here. Now, what I was explaining to you earlier, right, with this a sub I is equal to a sub j thing, this is where this comes into play, right? So what happens is that, note that this is relatively prime to n, right? So you can cancel them out. You can literally just cancel them out, right? This value here is relatively prime to n. It has to be relatively prime to n because it's inside of the set phi of n. Every element inside of that finite set is relatively prime to n. Okay, so that means, right, then it has an inverse. Okay, if it has an inverse, then we can cancel it out, right? We can multiply this guy by its inverse, and we can multiply this guy by its inverse, and it's going to cancel out. Okay, and so what we're going to be left with, right, is e raised to the phi of n is congruent to 1 modulo n. Okay, and so something that immediately occurred to me here, and actually this is what I asked the professor straight away, was that wait, why is it, right, that these two numbers have to be relatively prime to each other? That doesn't make sense to me, right? And obviously he doesn't do number theory, so he didn't really, he understood very quickly when he went to the proof, but at the time of asking him the question, he was a bit confused. But yeah, I definitely did not did not get why they have to be relatively prime. And so I knew, right, that if something is relatively prime, then that implies GCD equals 1 implies that it has an inverse. So I had an inkling that it has something to do with an inverse somewhere, but I just couldn't see exactly where or what, you know? And so then, right, what I was thinking was, okay, well, then that means then when you're encrypting, right, with RSA, right, because there's some message raised to something like that, right, does this value have to be relatively prime to n, right? I was like, doesn't that somehow, I don't know, that seems a bit weird, right? It seems to me that there are going to be cases where this is not the case, or this is not true, right? And then turns out then actually the true underpinning of RSA is Chinese remainder theorem, and it works anyway. They just use Euler's theorem sort of as a simplification. But okay, if you understand Euler's theorem, for the majority of the cases, it holds true, right? But for all the cases, Chinese remainder theorem got you covered. Okay, so now let's talk about decryption, and let's go over a proof for decryption. Now that we finally talked about the proof for Euler's theorem, I did all of that, right? I did all of that just to show you the proof for RSA decryption. So let's go here. So 6, and we'll close off with this RSA decryption proof. Okay. And so what we're trying to prove then is, where is it? Okay, I don't know if I can sort of yoink this out from here. Copy and paste. Yeah, we can do that. So we'll put this here, and I don't know where this came from. Okay, so we're trying to prove then that C, right, raised to some exponent d is going to give you the ciphertext m, right? That's a bit strange. strange thing to prove, I guess, but okay, let's do it, right? So what is m, right? What did we compute m as? So let's come up back here, and we said m was what was m? M was just the original value that you computed raised to e, right? That's quite literally what we did. So it's just m to the e mod n. Let's go down. And I'm probably going to, I don't know, should I write it out? I probably should, right? So we'll just do it like this, with this really, really huge marker here. So m was computed as, right, whatever your ciphertext was, m originally raised to the d power, right? That's how we computed c, right? Sorry, that's how we computed c. That's how we got this guy c. So c was computed as this guy here, right? So we're not proving the right side of this equation, which I don't know, for some reason I thought we were doing. We're proving the left-hand side of this equation, okay? So, okay, so we can substitute in that value, right? So we can substitute that in. So, and obviously all of this is reduced modulo n, right? So I'm not gonna write that out though. So this is going to be c, right? We're gonna substitute it in place for what we just computed here for m, and that's going to be m raised to the d power, right? And then obviously now we have to raise that to, it's not d, it's e, so it's my bad there. RSA encryption is you take the public key, not the private key, right? So it's m raised to the e power. So it's m raised to the e, all raised to the d, right? Reduce modulo n, of course. Okay, so that's really, really terrible, but okay, it's legible. Insert page after, and so now what we end up with is m raised to the e times d, right? And mod n. Okay. Now, what is this? What is this guy here? So now we can do substitution again, right? What is e times d? We actually computed this before, right? If you come up here, where are we? Somewhere here. Here it is. So, should be here. Yeah, e times d is defined as 1 modulo phi of n, right? That's the definition of the inverse, okay? So, let's start from first principles here. E times d is equal to 1 modulo phi of n. Okay, that's the definition, all right? Now, you should know, a modulus is obviously just division, right? We're just asking ourselves here, that, or we're saying, we can rephrase this as e times d divided by phi of n will give you a remainder of 1. So let's just write that out. E times d divided by phi of n will result in a remainder of 1. Okay, so this is all that this is trying to tell us here. And now I hope you know, right, that if we, whenever you're doing division, right, x, right, is equal to, okay, some quotient, right, quotient times your divisor plus your remainder, okay? So any division that you're doing, right, is going to be some quotient multiplied by your divisor, and then you're going to get a remainder as well. All right, and that, I think that's okay, like elementary school kind of thing, right? And if this wasn't entirely clear to you, then you can probably just like double check it for yourself as well if you wanted to. All right then, so e times d, right? E times d is equal to, right? What is the quotient? We'll call it k. It doesn't matter what the quotient is. We don't really care, right? Times d, which is phi of n. Phi of n, it's our divisor, plus 1. 1 is the remainder, right? Okay, 1 is our remainder here, remainder of 1. That's really what modulus is computing, just a remainder. All right then, so we've got e times d, right? So we can substitute it into this guy here, right? So we can come back here and say that m raised to the k, right, times phi of n plus 1, like so, right? Then finally, we can actually just factor this out, right? So this will turn into m times m raised to the phi of n raised to the k power. Okay, of course, all reduced modulo n, which I don't want to keep just writing over and over again. Alright, so you're probably wondering, I hope this is clear enough to you what's going on here, right? Obviously, you should know, this is like 7th grade math, right? This m here, whenever you're multiplying exponents, you just add them, right? So m times n, you add 1. So this is where the plus 1 went, right? Came out, became an m, right? And then when you're multiplying exponents, then exponent to an exponent is equivalent to multiplication, right? And so that's what happened to this guy here, right? So what we're doing is we're taking an exponent to an exponent, right? Which is akin to multiplication. So I hope that's simple enough to follow. And now this is where all our work on Euler's theorem just comes into play, right? Look at this guy here. What is this, right? Of course, all of this is modulo, reduced modulo n, right? And so, but what is this here, right? And based on Euler's theorem then, right? If m and n are relatively prime, right? Then m raised to the phi of n is equivalent to 1, right? Okay, so that's it. That's the great idea. Of course, reduce modulo n, of course. And you know then already why they have to be relatively prime. And this is what I was telling you before then. Okay, does all the m you have to pick be relatively prime, right? Well, isn't that like an issue or something? And then it turns out, okay, it works anyways via Chinese remainder theorem. And so what this turns out to be is just m times 1 raised to the k power, right? Mod m. Okay, and then this just goes. So what we're left with then is m is congruent, right, to m mod n. And so we've successfully proven that RSA decryption works, right? So we were able to recover our original plain text. Okay, so that was a bit much, I think. Not really though, but I hope at least you were able to learn at least a little bit of the underlying mathematics behind RSA and asymmetric cryptography. And obviously, right, pertaining to a little side note on cyclic groups, right, this is just like one kind of cyclic groups. Anytime you have a cyclic group, you have a basis for a crypto system. And there are other kinds of cyclic groups as well, right? And okay, I won't be getting into that here, but it definitely, I think, gives you a strong foothold if you understood all or perhaps most of this. It gives you a strong foothold to just, keep studying asymmetric cryptography from here. In my case, I think I have just about everything I need to go ahead and just make my RSA hardware implementation. So yeah, and obviously I don't think I needed this really to make the RSA hardware implementation. I sort of just needed it, I don't know, psychologically at the very least. Anyways, I think that's enough from me, yeah.